Yeah, so this is the so we converted that equation, second order nonlinear equation, into the first order system, to first order differential equations. So theta 1 was the angle, theta 2 is the angular velocity. Okay, let's draw the phase plane. Yeah, phase plane. This is the phase plane because we are dealing with two-dimensional system. We have two state variables. First one is the angle. Other one is the angular velocity of the variable. All right. So, so let's take an initial value. So x, let's say theta 1 of 0 and theta 2 0. This is the initial value. So for a for this initial value, there's a trajectory passes through this. So in general, so this is called the trajectory or path. If you drop a particle at this place, so if the vector field is in this direction, right? Vector field is in this direction. The particle goes along this trajectory, right? Okay, so this is called the trajectory. I will write that down because you are the first time you hear that word trajectory. This is called the trajectory path. So if you drop a particle into here, if the vector field is in this direction, right? So that particle flows along this trajectory. Let's consider, so this is t equals 0, and this is a general point. Yeah, t equals t. At that time, the state variable would be t sub 1 at t, sorry, t sub 2. So this is called the trajectories, right? So particle, if you drop a particle into this position, into t1 of 0, t1, theta 2 of 0, if the vector field in this direction, the particle flows along this trajectory. And this is a general position, right? General, when t is equal to t. Then these are the state variables. If you choose a different initial value, initial position, let's say theta 1, let's say dash, I will say like this. So this is a different initial position, right? Dash, and there's some, there's trajectory passing through that point. This is another trajectory. This is another trajectory, right? When you change the initial position, you get different trajectories. So this phase plane is completely filled with different trajectories. If you change the initial position, you get different trajectories. But these trajectories never cross each other, right? So they are parallel to each. They are, yeah. So they never cross. So we will prove that. Because of the excess uniqueness of the solution, they never cross. These trajectories never cross each other. If the vector flow is in this direction, yeah, if you drop a particle at somewhere, let's say here, that particle travels along this trajectory. Okay. So to investigate these trajectories, right? So by investigating these trajectories, we extract the information, the hidden physics of the problem. So by analyzing these trajectories, we analyze. So remember, in your second year, you analyze the behavior around, let's say this is a periodic fixed point or equilibrium point. And you showed, you proved that, yeah, this is a periodic fixed point. Then the trajectory around this point is going like this. By analyzing these, when they never cross each other. So we can study the trajectory around the trajectory to extract the physics of the problem. So if you want to extract, or if you want to find the details, or if you want to find the information about the solution, you have to investigate the trajectories. If you look at these trajectories, okay. So here you have a periodic equilibrium point. So this is moving. If you drop a particle into here, so that one is the particle is circling around this point. Yeah, they never go anywhere. They just repetitively circling around this path. Yeah, right. So you have to study these trajectories to find or extract the information about the solution. Okay. So in this course, I think I mentioned earlier, we draw phase diagrams. Using phase diagrams, so we can get an idea about the solution. Okay. So here, the most important thing, if you have a system like this, without solving this system, we just study the trajectory. We investigate the trajectory without solving the equation, right? Then we can find information about the solution. Okay, so that is the Poincare approach. That approach is called geometric approach, right? So he did not solve the equation. Without solving the equation, the idea is to investigate the behavior of the trajectory. So we have to investigate the behavior of the trajectory. If you have this behavior, so this one has a periodic equilibrium point. So this one moving away from this point, let's say you have a point, equilibrium point. So everything flowing away from this point. This point is unstable. You always study these trajectories, right? By studying, by investigating those trajectories, the behavior of the trajectories, so we can find the information about the solution without solving the system. Okay, so this is the Poincare method. So then I think next week, I think, yeah, so later I will discuss this. Yeah, so time another 30 minutes. Okay, so yeah, let me cover this part as well. So before that, just let me x depends on t. So let's say if you have n order differential equations, then you have to, yep, so this one. So then you have to introduce how many state variables? N number of state variables. Okay. And, okay. Then so you have n number of state variables. So this system is called n dimensional system or nth order. So yeah, so you can write first order differential equations. Yeah, using these state variables. So then basically you can write this first order system. Yeah, the dynamical system. Yeah, this is the dynamical system. Right. Right. So this is called Xn, and T is the T is the independent variable of these state variables, right? I don't mention that here, right? So this is called this system is called n-dimensional system or nth order system. Nth order system. Okay, so we already know this. So let me discuss. Because we have time. Yeah, because we have time. Let me discuss the difference between autonomous and non-autonomous systems and third system. So what is autonomous system? Yeah, non-autonomous. Yeah, so let me discuss that. If you have, so far we have discussed autonomous system. That means, so far, these kind of systems are called autonomous systems. These kind of systems are called n-dimensional autonomous system. Why? It doesn't include any explicit time dependence. That means, so if you have explicit time dependence like this, yeah, this is non-autonomous. This is, autonomous. This is autonomous. So it doesn't include any explicit time dependence. This is called autonomous endemic. Yep, so autonomous system. Autonomous. For instance, non-autonomous systems. So it is given here. Here we go. Yeah. So earlier one autonomous, no explicit time dependency. There is no t terms. If you have this, so this is if you have t term explicitly expressed in the equation. So this is non-autonomous. But here we don't have any t terms. So this is an autonomous system. But if you look at this example, okay, so here we have x term, x, but here we have t term explicitly, right? So this is an example of non-autonomous system. This is an example of non-autonomous. This is non. All right. I think, yeah, so that's, today is the first day. I think that's enough for today, I think. Otherwise, we will get confused and to do it physically. Yeah, so I don't know whether you didn't answer my question. Yeah, you didn't talk to me much. Yep. So any questions up to this point? Did you understand the autonomous and non-autonomous difference between autonomous and non-autonomous? Yeah. So here we don't have any t terms. Yep. So this is an autonomous system. Autonomous system. These all are autonomous systems. If you have a t term explicitly here, explicitly. තනියම තියෙනවා T. So this is a non-autonomous system. Yeah, any questions, any doubt?